Then comes the heat balance sheet. Heat balance sheet, mainly the purpose of most tests is to develop the or to prepare the heat balance sheet. Heat balance sheet is a simple a table which conveys us what amount the total amount of heat supplied by the fuel goes in what fraction to what parts. That is, we know that when an engine run, it needs to be cooled. Also, the surrounding air takes a certain amount of heat from it, and the exhaust. We know that the fuel, which is at normal temperature, say at 25-degree temperature, when comes out of the engine after burning or doing its work in the engine, its temperature increases. That is the temperature of emission. So, some amount of heat is carried away by the cooling water, some amount of heat is carried away by the emission or by the exhaust gases, some amount of heat will be lost to the surrounding or to the surrounding air by convection and radiation, and fraction of the heat supplied to the engine will be used in order to develop the output, which we call it brake horsepower. So the heat balance sheet is simply is a procedure to know what fraction of heat supplied is carried away by the cooling water, what fraction of heat supplied is carried away by the emission, and what percentage of it is converted into useful work. So the basic purpose of preparing a heat balance sheet is to know about the various fractions of heats, uh, what we get from the total heat supplied. The useful heat supplied we get the amount of useful heat supplied can be calculated by taking into account the brake horsepower. So first of all, in order to prepare the heat balance sheet, what we have to do, we have to calculate all of the heats which are going in various parts. Suppose what fraction is converted into useful work, and what fraction is taken over by the cooling water, then what fraction is goes along with the exhaust gases, and then radiation loss. So from the screen we can observe the heat balance sheet. What is its purpose? Its basic purpose is to know how much amount of heat is converted into useful work. So it is used to compare the performance of other engines or different engines with each other. The performance of an engine is usually studied by heat balance sheet. I have to explain to you. The performance of an engine is usually studied by heat balance sheet. The main components of heat balance sheet or heat balance sheet are: the very first, heat equivalent to effective work of the engine or brake work of the engine. Second, heat rejected to the cooling medium or cooling water or coolant as the case may be. Third, heat carried away from the engine with exhaust gases and unaccounted losses. Fourth, the unaccounted losses include the radiation losses from the various parts of engine and heat lost due to incomplete combustion. We know that the combustion in engine, the total whatever the amount of fuel is supplied to the engine, the total amount of fuel does not burn. Some amount of it remains unburned. It may range from 2 to 5% in case of petrol engine and 1 to 2% in case of diesel engine. So the amount of fuel what we have supplied to the engine but actually does not burn in the engine will not produce any power, and corresponding to that amount of fuel we have to reduce how much energy has been gone has gone without harnessing. The unaccounted losses include radiation losses from the various parts of the engine and heat lost due to incomplete combustion, which may happen both in diesel and in petrol, as just explained to you. The friction loss is not shown as a separate item to the heat balance sheet, as friction loss ultimately in this very heat balance sheet, as the sentence, what is the sense of this very sentence? The friction loss is not shown means a separate relation for friction loss or power lost in friction has not been shown, because the heat balance sheet, the friction loss ultimately appears in the form of heat, which is taken away by the cooling water, exhaust gases, and by the radiation losses. The first of all, heat supplied by the fuel. When when we burn certain amount of fuel, it gives an amount of energy to the engine that has to be converted, or that will be absorbed by the engine in its various forms. The first form of the heat is for total amount of heat what we supply to the engine, total amount of heat which is supplied to the engine. In this case, because we have taken the case of petrol engine, but it can also be written for diesel engine, let suppose mf is the mass of fuel which is burned in a given time period, suppose in 1 minute, suppose in 30 minutes. C is the calorific value of the fuel. It is that amount of energy which we receive by burning of 1 kg of fuel, that is calorific value. Then the heat supplied by the fuel, when we burn 1 kg of fuel, certainly we will get the heat by burning 1 kg of fuel as mf mass of fuel multiplied by C calorific value. And for gas engines, if V is the volume of the gas supplied per minute at natural temperature and pressure, and C is the calorific value of gas, because we know that for liquid fuels the fuel is measured in kg, and for gases it is measured in volume. Then the heat supplied to the gas engine per minute will be equal to the product of volume of the gas consumed by the engine and its calorific value. Then the first part of the engine output, or that fraction of the heat supplied which get converted into useful work, is heat equivalent to brake power is equal to brake power. The brake power what we get from the engine by Morse test is then multiplied by 60. 60 has been multiplied because it is kilowatt hour, because we are taking the case of fuel burnt in 1 minute, and the power calculated will be per second. So in order to convert into per minute, we have to multiply it by 60. Heat carried away by the cooling water will be taken as QW. QW is further equal to MW CW T0 minus T1 kilojoule per minute, where QW is the heat carried away by the cooling water per minute, MW mass flow rate of cooling water in kilogram per minute, CW is the specific heat of water which is mostly 4.18 kilojoule per kg Kelvin, T0 outlet temperature of the cooling water, T1 inlet temperature of the cooling water. Inlet and outlet temperatures are measured by inserting two separate thermometers in the inlet hose and outlet hose. T0 temperature will be recorded by that very thermometer which has been inserted in the outlet hose of the cooling water, and T1 is the temperature recorded by that very thermometer which has been inserted in the cooling water hose at inlet. Then comes the part fraction of to heat supplied, which is again heat carried away by the exhaust gases, or heat carried away by the emission, or we can say that by the smoke or exhaust. Heat carried away by the exhaust gases per kg of fuel is given by this very relation as shown on the screen, QG. QG stands for mass of exhaust gases formed per kg of fuel supplied. How much emission we get, or what is the amount of the exhaust gases that is measured, and it is set equal to this relation where T, G, Ta are temperature of exhaust gases at exit and Ta is the temperature of air or surrounding air. We know that the temperature of fuel and surrounding air are almost equal, or the difference may be slight, so it is taken equal to Ta. Tg, temperature of the exhaust gas, it is measured by a thermometer which is inserted in the silencer or at the emission at the exhaust at a pocket made in the exhaust. Cg, specific heat of exhaust gases, which is taken in kilojoule per kg Kelvin, and mg, mass of exhaust gases, I told you earlier. Qg, heat carried away by the exhaust gases per minute. In this way, by using this relation and once all the other parameters are known to us, we can calculate the heat carried away by the exhaust gases. Then the next part is heat carried away by the surrounding air. Now it is the radiation loss, which may be because of convection and radiation. This loss is difficult to measure directly. What we do, we have the total amount of heat supplied to the engine. We are having all the other terms, that is heat carried away by the water, cooling water, heat carried away by the emission, and the fraction of the heat supplied which is converted into useful work. What we have to do, we have to subtract the all other parameters, that is heat carried away by the cooling water, the heat equivalent of useful work, and heat carried away by the emission from the heat supplied by burning of 1 kg of fuel. Then the difference will be equal to the heat carried away or heat lost to the surrounding air by convection and by radiation. Then as we see, as we observe from the screen, the heat lost to the surrounding air by convection or radiation, that is E, will become equal to A, total heat supplied to the engine by burning a certain amount of fuel, minus B, useful amount of work which we the fraction of energy which has been converted to useful amount of work. C, heat carried away by the cooling water, and D, heat carried away by the emission gases. From this very relation, we can get the heat lost to the surrounding air or heat lost because of convection and radiation. As we can observe from the graph, the energy on one side, the percentage of energy has been shown, that is what amount of energy is converted into useful work, what amount of energy is carried away by the cooling water, and what amount of supplied energy is taken away by the exhaust gases, and then what amount of energy supplied is lost in form of radiation losses and incomplete combustion. You can observe from the engine speed of engine along the abscissa. We have given the engine speed in RPM at 1000 RPM, 2000, and then all other speeds are shown. In this way, on the other side, the total percentage or total fraction of energy has been shown, and it at 100%, 0 to 100%. Useful amount of work has been shown at the bottom. You can observe that with the increase in speed, the useful work also increases, but after reaching its maximum value at around 3000 RPM, further it decreases. Then the next part is heat carried away by the coolant or by the cooling water. From this very table, engine speed or type of engine, SI engine, against the SI engine, CI engine, compression ignition, SI spark ignition, that is petrol engine, CI compression ignition means diesel engine has been shown brake load efficiency. It ranges from 21 to 28% for SI engine. That is, it is that amount of energy, which that amount of the supplied energy which has been converted into useful work. Then the heat rejected for SI engine to the cooling water in percentage form, it may range up to 27%, and heat rejected to the exhaust gases may range up to 30 to 55%. And unaccounted losses, it range for a petrol engine or CI engine 3 to 5.5%, including incomplete combustion loss. And then for CI engine, the efficiency, that is the useful amount of work, what it is the fraction of the heat supplied what we have get. It ranges from 29 to 42%. That is, the CI engines are more efficient as compared to SI engine. We can observe it from the table. Its range from its efficiency or its range from 29 to 42%. Heat rejected to cooling water in case of CI engines, diesel engine, ranges from 15 to 35%, and heat rejected to exhaust gases may range from 25 to 45%. And it can be observed from this very table, the heat lost to the exhaust gases or heat carried away by the lost gas to the exhaust gases is more in case of SI engine as compared to CI engine. That's why the CI engines are more efficient as compared to SI engines. The last unaccounted loss is 2 to 0%, 0 to 2%, including a incomplete combustion loss of 0 to 0.5%. Thank you. I hope you have taken or you have understood what I have told to you, and in case you want to know something more about it, then you can contact me at my phone number 94173 97096. Baljeet Singh Virk. Thank you so much.